Hello again. Once more, I'll be looking at SIG language. And yesterday we got to the many item pointers. And it looks like it's a pointer to an array of pointers, maybe. But let's go through it and see what we can figure out. We were looking at the example. In this example code, we've written a function that can take a buffer of any length. Yes, notice how a single item pointer to an array of code of bytes coerce into a many item pointer of bytes. Oh, so we are converting a pointer to an array to a pointer. What was it called? Many pointer? Many item pointer. So we have a pointer to each element of the array. Is that what's going on? Let's take a look at it. Should we do as we've done before? Just copy it here. Let's take a look at what the test, if the test succeeds, we can write out some information. So we are making a buffer. And this one was the repeater. So we have this repeated 100 times. So we put in 1 in every location. Then we make a buffer pointer. It's a pointer to this type. And this type was what this buffer was. And then we have a buffer many pointer. So we're just setting this one to this one without any form of casting or anything. Double all many pointers. Buffer many pointer, pointer buffer. Oh, that was this one. So it takes in a many pointer and the length of the buffer. Let's look at this one. Buffer. We have the many pointer and the size. Yes, the size is 0, while I is less than the buffer, the byte length. Yes. Increase I by 1 and buffer I times 2. Again, it's a bit weird for me how the conversion between this from this and then compared to this notation, which is really weird to me. It probably isn't. Somebody's probably had some thoughts about it, but to me this is kind of weird. But let's see. This looks like the most normal code I've ever seen, so that's not an issue. It's more the conversion between, or the way to access it is kind of weird. Okay, for buffer, expect everything to be 2, yes. First element, see, this is what I'm talking about. Here we have a pointer to a buffer, and we take the content of the location. Right, how was it? We were going to say it when it was an ampersand, that this is the address of the pointer and then indexing into that. I think that the the pointers and addresses and many item pointers are gonna be the most difficult part for me, because it's not something that we use in higher level languages. We just have buffers that you index into. We normally don't point to specific elements. But yeah, it makes sense. But it's the conversion and the way to access the content. So I'm not sure about the differences, because if we can access it through this, then we could have done the same instead of casting it to this one, which also is weird. It's casting it without any casting keywords. But again, this is just an overview to understand what's possible in the language. It's not an in-depth understanding of the language itself. I just need to know what is possible in the language before starting a project where I have to learn the different elements. So let's move on to slices. Coming from Go? Nope. Slices can be thought of as many item pointers with a length of usize. There we have this weird usize. Just wanted to make sure the mic was actually not muted. Okay, the length of usize. These use the syntax. Yeah, that's the many item pointers. Slices are easier to use safely and more convenient than many item pointers, as they store the valid length of the buffer with them. So that means that every time we make a slice, it also contains the length of the slice. Slices are sometimes referred to as fat pointers, okay, as they're typically double the size of a normal pointer. Slices are the most common way to pass around buffers in SEC. Why are they typically double the size of a normal pointer? Oh, okay. Not each element, the size of the slice. So I guess that the slice contains an address and a length, and that's why it's twice the size. Unlike many item pointers, for loops works on slices. The syntax, square brackets n to m, is used to create a slice from an array, an operation known as slicing. This creates a slice, a view into the array consisting of pointer and a length. Slicing includes the first element n, but excludes the last element m. Okay, so I guess this is 0, 1, 2 and not 0, 1, 2, 3, as we had in the other example. Where was it? We had this one, where we have 3 dots, which apparently means include both, but strangely enough we can't use two dots. But here we can. Const array. So this is a way to initialize an array, as we done before. And here we can take the array. Oh, okay. Now the things are coming together. This is not a keyword. This is the variable or the array that's containing these elements. So we are taking elements 0, 1, and 2, 0, 1, and 2, and together they add up to 6. Again, wording, if you're making an array, yes, it's nice that you're calling it array, but you can be confused and think that's a keyword or something. But again, read the line. Read the goddamn line. When these n and m values are both known at compile time, slicing will actually produce a pointer to an array. This is not an issue as a pointer to an array. This is not an issue as a pointer to an array will coerce to a slice. An array pointer. Yeah, it's these notations that is throwing me off. But that's okay. They will come. No need to get frustrated. And here we have the same again. We make an array, we make a slice, and here we take a pointer to a const of 3 elements of U8s, and that is the type of the slice. The slice will be of this type because it's converted to this array of types under the hood. Because both values are known at compile time. Syntax x of square brackets and a dot can also be used when you want to slice to the end. Oh, so if you want to take all elements from a certain index to the rest of the elements, then you just do this instead. I want to do a test on this one. First of all, test if it works. It did, because I want to. Yeah, now it is at compile time, but if I do a variable and set it to something. Wow. And then use the index to do this. Will this still work? Why is it complaint? Oh, it's because it doesn't change. Index plus plus. Isn't that possible in SIG? It's not? Okay. I thought they adapted that notation as that's used in all kind of languages since C++. But okay, I'm trying to force this not to be known at compile time, but I guess that the compiler will be smart enough to know, right? If not, we need to take some random number, or we did something where we read outside. Yes, this one. We could do something like this, then it won't know it at compile time, that's for sure. So we're just gonna call this the index, and then remove this one. Oh. That wasn't very smart. Let's say 10. So now we have an array of these 6 numbers, but we're reading at location 10 out here. So this is undefined behavior. And we have now an index, and I'm gonna, that might not be smart. Can we do something like this? So we're sure that the value will be within that index, but now it's not known at compile time. It really didn't like that one. The variable type comptime int must be const or compile time. Index equals 3. Oh, okay, so it's not dependent on. This is not an issue. Boop, 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 there it is. When these values are both known at compile time, slashes will actually produce a pointer to an array. But it's not possible to create it without knowing these two at compile time. That's kind of what I'm seeing here. It's not that it could do it, it's that it can't do it. Should we try to change the length of the array instead? So that also changes the type as I see it. So we can just do something like this and then use the index for that one instead and say the first 3. Then we're going to pick a number between 0 and 5 from some unknown memory, make a new array. We have no clue how long it's going to be because it's generated at runtime. And then we see if it converts it to a slice. Nope, still not. Index outside of an array, yes. But that was something we were allowed to do if we added this one. Yeah, and what does it say? Index outside, set runtime safety, false. Why am I not allowed to do this? This allowed me to do it. Yeah. So why am I not allowed to do it now? It's the exact same thing I'm doing. Stop being a hassle here. What is the difference? I'm reading at index 5. The only thing is that I'm jumping in between or having an in-between variable defined. So I just have this. But it shouldn't make a difference. If I use a const here, or I use a variable, I should still get whatever is at index 10. I know it's outside the array. That's kind of the point. I want the unknown behavior. It really do not care. Okay. Doesn't matter. I just wanted to test to see that if it didn't know it at runtime, that it wouldn't, this slice wouldn't be of this type. But yeah, let's delete that one. Can also use Let's again compare our pointer types. Oh my god. Pointer to a type, pointer, item, oh, what was it called? Many item pointers. Many item pointers, and what is this? Or was that that was the many pointer type? So we have, oh my god. Okay. Indexable. So these three can be indexed into. They have the index square bracket notation, so that's nice. So we know that if we have a square bracket, we can actually index into it. Sliceable. All that can be indexed can also be sliced. Element count, always 1, as it's a pointer to an address, or to a type in the address, a pointer to a type somewhere in memory. Okay, it has to be compile time known. So, okay, so that's why we can't do anything like what I wanted to do, because it's not possible. It needs to be compile time known. Element count unknown. That was the many item pointer. So we don't know the count. Okay. But we can still index into it. So is this the most unsafe pointer type? It might be. And this is runtime known. An array to a type. Arithmetics. No, no, yes, you can step through. Does that make sense? I think it does. Sizes. Size of usize, 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 usize times 2. Attributes. I'm not sure what they mean by attributes, but fair enough. We can now apply our knowledge and make another program together. Oh, I missed that. They probably had some small programs you could do while learning this, but let's jump on to Enums. Finally, something that's a little bit more understandable. Enums allows you to define types with a restricted set of name values. Let's declare an enum. Very straightforward. An enum consisting of the 4 corners of the world, north, south, east, and west. Enum types may have specific integer tags types. What is a U2? Unsigned integer of 2 bytes or bits? That would be kind of weird. But why not? Enum ordinal values start at 0. They can be accessed with the built-in function int from enum. That is really nice. That's something you can always use. So we are not casting it like in other languages directly. We have I don't know what you're going to call these, ampersand and a name, if they're kind of functions or they're cast thingies. But yeah, again, naming of stuff. While values can be overridden when the next value continues from there. Oh, okay. Yes, so we can just override what they would have been by default. And the next one will be this one plus 1. I've learned to do this from an earlier employment. So you always have room to add stuff and never leave them without an a value because the value is needed. If you're working with databases and stuff like that, and you change a value or add something in between, all the values won't match up with what you have in the database. So always use some numbers you define and don't ever change them. Enums can be given methods. Okay, that's a new one. These act as a namespace function that can be called with the dot syntax. So we can have suits dot is clubs. What? Suits spades. That's this one. Is clubs is equals to suits is clubs, and give it dot spades. That's a weird notation, this one. So you're calling the function, but you haven't given it the enum itself, so you give it the enum itself. That's kind of weird, but fair enough. Enums can also be given var and const declarations. These act as namespace globals, and their values are unrelated and unattached to instances of the enum type. You can do what? So you can make an enum that has some predefined values, but you can also add a variable to them. But okay, so they are global namespace globals. So this is like static in other languages. The values are unrelated and unattached to instances of the enum type. That is kind of weird, but I do like it. I'm not sure where I would use it. Yeah, because this handles that variable alone. Yeah, I've been coding in Kotlin too much. They have values and vars. Yeah, so you just have that. I like that. Again, I have no clue where to use it, but you could use it for, I don't know, some memory type or management. So you have this, is it assigned, is it not assigned, how many is assigned. You can just check. Yeah, I think that would be, I've never seen that before, but yeah. Structs. Structs are six most common kind of composite data type, allowing you to define types that can be stored, that can store a fixed set of named fields. SIG gives no guarantee about the in-memory order of fields in a struct or its size. Like arrays, structs are also neatly constructed with type, curly brackets syntax. Here is an example of declaring and filling a structure. Yeah, so we have the definition of struct. It's a vector 3, x, y, and z, a floating point, 32 bits. And when you instantiate it, or construct, what do you call it? Instantiate it? Declaring and filling, declaring and filling, declaring and filling the struct. Cannot be implicit initialized. No, that was one thing I came upon last time I worked with SIG, or tried to, was that you cannot initialize a struct or fill a struct with some of the values. You have to define all the values. Yeah, this will give an error because it's missing the y. Fields may be given defaults. Then you can do it. Oh, see, that's good to know, because you can just give everything a default value, so you could actually construct this without even giving it anything. You could just instantiate it. Do we then need the curly brackets, or could we just do something like this? We can. So we can actually just say that this is my vector dot Is that possible? Are they variables or values, or what are they? That is also allowed. Like enum structs may also contain functions and declarations. Structs have the unique property that when giving a pointer to a struct, one level of the differencing is done automatically when accessing fields. Notice how in this example, self.x, self.y are as accessed in the swap function without needing to difference the self pointer. Y swap. Yeah, it has the self ability. Nice. But why are we not telling the struct if we are talking about values or const? Or can't we do a const in a struct? Couldn't this be a... Nope. That is not allowed. So we can't have a const value in a struct. That's... I would like to, if you want to have a constant of something like pi in a struct about circles or something, it would be nice to have pi defined as part of the struct. So when you add a function to calculate some stuff on it, you always have pi available. So why can't we have... We can't even call it var, right? No. After declaration. Well, that's something I would like to figure out, because of course I can do pi float 42 equals 3.1415. Something like that. And then have this. Do we have to have this notation? No? Then why are you now saying that this is not correct? It has the X. It's right there. Pi. That's weird. Come on. So now you don't see this. This is what I'm talking about, where we didn't really change anything, did we? I don't think we did. Come on. No? Struct main vector 4 has no member named x. What do we call that? That is to me an x value. It doesn't have a y value. What's going on? Let's do this, because at this point it has been working. Now it's just being annoying, because now I'm not even accessing the member x. And that's where I have no clue what to do. Can't I just delete this cache, move to trash, and then try again and see if it simply do not want to work. That is so weird. See, right now I would really like somebody in the chat to just say, hey, it's because you haven't reset something or whatever it could be. It there's really no reason why this shouldn't work, and it's worked before, so this makes absolutely no sense. Can we do the typical, have you tried turning it off and on again? No. What about a different test? This one, that works. This doesn't work. Why? Okay, we're gonna copy paste it once again. Paste it in, run it. Now that works. If we take this, do this, it still works. Hi. Let's see if I can. Now it's saying that's not right. Error expected. Type found. Compile time float. Oh. Okay, fair enough. Float 32 equals. That's fair enough. That still works. Let's see. And now it doesn't. Is that because I'm doing this? What if I do this? No. If you are initializing pi equals 10, it's dot pi. Like this. then it still doesn't work. I find that extremely weird. Just because I add another value, then why does it do this to me? Yeah, because this is needed. It shouldn't be needed. Pointless discard of local constants. Why is this not working? Cannot assign to constant. Oh, now it's not angry about it's not existing. It's actually angry about cannot assign to constant. Squeeze me? Oh, we are still done here. Now we can take this one. That's possible. But there's this with structs, as I understand. You can't change the values, you have to change the entire struct, right? So we can access it, but we can't reassign it. They are defined as const. Error cannot assign to const. So everything in a struct is defined as const. But they didn't mention anything about that, right? No, we can assign it on when we fill the structure. We can fill the structure. Missing fields. Yes, if we don't fill out everything. Like enum structs may also contain function and declarations, just like the other one. Structs have the unique properties when given a pointer to a struct. And the value as its field. Yeah, we saw that. But okay, they do not mention that structs are actually const data. Can we access it by creating a pointer to it and then writing directly into the struct? How do we make a pointer to? So we have a variable named vPoint, which is equal to, what could it be called? A pointer to the address of const vector for pointer. Yes, that looks right. And then vPoint. This cannot be indexed, could it? No, because how would it know what this means? It wouldn't. Then it would be something like, I don't think we can do that, can we? No. Does not support indexing. No, because that was what we saw before. That this, as I understand it, if we jump back 2 slices, we have a pointer to a struct and we can't index into it. But that's good to know. Structs, unions. Did I skip something? Structs, no, unions. Unions, what are unions? Sig unions allows you to define types that store one value of as many possible type fields. Only one field may be active at one time. Oh, I hit upon that before. That's kind of clever, but I think it's this idea of when you look in memory, you just have bits. How you read the bits. So I'm gonna conclude something before I read it, that if we have this, the one that is the biggest defines the size of the union. So here we have a float of 64 bits. We have an integer of 64 bits. The Boolean is 1 or 8 bits. So the biggest are these two. They are the same size. So this union will just be 64 bits in memory. So it would just be a 64 bit in memory, but how you read it is what this ensures that you can read it as an integer, float, or Boolean. But let's see. Bare union types do not have a guaranteed memory layout. Because of this, bare unions cannot be used to reinterpret memory. Accessing a field in a union that is not active is detectable illegal behavior. So results, again we have a weird notation here. But let's just run this one. Yep. Oh, I would expect that to be an error, but it is not. This might have changed from version 13 to 15. Because that was just accepted without any issues whatsoever. Let's just write out what it's actually converting to. Because I want to see that result. It makes a result of integer of this and then sets the float value. It only sets the value. But let's see what's actually in there. This, is this still a D? Might be. Let's just go to the SIG learn language reference. I know it was here somewhere in the beginning. There it is. We actually want to write out a float. So what do we use to write out floats? It's not there. So I don't know. I would say let's try with D. And now it fails. I really hate it when it's not consistent in what it's actually doing. We just tested it a couple of times and it worked. And now it doesn't work. This works, yes. So as soon as you say this is an int, then it's an integer. But it could have been a Boolean float. Okay, let's get back to this one. Okay, so now it does adhere to this one. Tagged unions are unions and use an enum to detect which field is active. Here we make use of payload capturing again to switch on the tag type of a union while also capturing. Oh, okay, so we can actually, without having to do some reflection, we can use this tag to figure out what type is in use. So we call it A, B, or C. A is an unsigned, a float, and a bool. Switch on tagged unions. We make a tag of the type B, which is a float. We give it a value. We switch on the value. And if it's of type A, B, or C, we handle it. Again, this notation is really, really hard for me to read right now. Why are there pipes? And why is this pointer to a byte? Why is it not U8? Because it can't be a U8. I don't know why. Is it because of this? No. Shadows. Okay. Probably. Here we use a pointer capture. Capture values are immutable. But with the pipe pointer value syntax, we can capture a pointer to the value instead of the value itself. This allows us to use deferencing to mutate the original value. So we get the value, we get a pointer of that type, and then we access it. Okay. Keeping it all in your head at one time. This notation we've seen before, that's just the access of the value. Here we are apparently doing a capture of a pointer instead of the value itself. We do a capture of the pointer to that value type, and then we access it and add 1. Damn. I think it's going to be hard to figure out when to use what kind of pointer. The tag type of tagged unions can also be inferred. This is equivalent to the tag type above. Void member types can have their type omitted from the syntax. Here's none of the type void. Okay. So this, if we just do this, yeah, this should still work. Okay. And what if we add D as a float 64? Would that still be just doing this? How does it know? That's kind of impressive, but I guess that it sees that it's switching on a tagged which is this one. We are saying that it's defined by union, a tagged union, which has these values, so it knows that if it sees D, it's a float. And that's a Boolean, and that's, yeah. Nice. But then I'm kind of confused why we would ever have an enum besides the union. Why not use the notation like this one? I expect that these values should match these definitions, so it doesn't make sense to ever use this. But maybe there is a reason for this, but it seems kind of weird that we have this one. But okay, it worked, it makes sense for once. The only thing is this. What was it called? Pointer capture. Integer rules. 6 supports hexadecimal, octal, and binary integer literals. So we can initialize it by normal, decimal, hexadecimal, hexadecimal. Why show this twice? Oh, to show that you can do it by capital letters as well. Octa numbers and binary. Nice. We can also do it. Underscore may also be placed between digits as a visual separator. I use this a lot. I really like the idea because you can, split it up by how many bytes you're talking about. You can switch it. You can use it to indicate this. At work, we do simulations of 1 billion at a time. And it's really nice to have these separators to make it really clear that you're not mistyping anything and you actually add 1 billion and not 10 billions or only 100 million. A waste of time if you do a run and it isn't the full number, expected number of iterations. Integer widening. Oh god. Integer widening is allowed, which means that integer of type may coerce to an integer of another type, providing that the new type can fit all of the value of the old type. Yes, so we can expand on it without any issues. We can put an 8-bit value in a 16-bit value and a 16-bit value in a 32-bit value. That makes perfect sense. There's room for it. We do not lose any information. If you have a value stored in an integer that I cannot coerce to the type that you want, add int cast may be used to explicit convert from one type to the other. If the value given is out of the range of the destination type, this is detectable illegal behavior. Oh. Okay. So this is allowed, but if I say 2000, this is not allowed. But how do you force it to do this? If I just want the lower 8-bit, can I do something like this? No. Why not? Why not? I know this type is of a 60-bit value, but I make sure that it can fit inside an 8-bit value. So why is this not allowed? If I did something like this, that's allowed. So maybe the percentage isn't used for mod in SIG. If it has that implementation. Yeah, it does. Oh, maybe it's called rem. I'll try to use that one instead. It actually exists. Let's try that one. Nope, it doesn't like that. And then it does. Oh my god, that's annoying. So if I do this, now it works. There's something weird going on here with the visual code setup, or me forgetting to save before running it, or something is off. It still works. And that would still work because it would be a 0. But if I do this, yeah, then it breaks. Okay. So it makes sense. But so right now it supports both the binary operator. It's a binary operator. That's back in 2017, so we can't really trust that. But okay, we can cast as long as we ensure that the number we are casting can fit inside whatever type we are casting to. So if we do this, save, run it, it works. Yes, perfect. Integers by default are not allowed to overflow. Overflow are detectable illegal behavior. Sometimes being able to overflow integers in a well-defined manner is wanted behavior. For this case use case, SIG provides overflow operators. Normal operator, wrapping operators. That's a new one. How does it handle signed integers then? Let's take this one. Can we output the A value? It doesn't output anything to the debug print. Annoying. Do we have this file output here? Yes, it does. But then we can't convert the value. Okay, fair enough. And we don't have debugging set up yet, so we can't even use that. I would have liked to play around a bit with this one because this is unsigned. So if we say this and 127 plus 1, I can never remember. There, this should be minus 1.7, right? Save, run. No. Well-defined overflow. I have no idea what it's actually failing on this, or yeah, it's failing on this one. But what is the value? Is it 128? I think there's some, we add 1, but what is the value right here? I would just like to output the value of A at this point. Maybe for next time. This has been a bit over an hour, so I will have to go. But as always, this will be posted on YouTube as well. So if you have comments or things that could help me understand some of these weird behaviors, then please comment. It would help me learn. So please help. Thank you. And until next time, see you guys around.